Hello everyone. In this video, I'm explaining about what is permutation group or symmetric group. See here, you take a set with n symbols or set of n symbols. S is equal to, I'll take those n symbols as 1, 2, 3, so on up to n. Then you have to collect all bijections from S to S. So, all bijections from S to S. Collect all these bijections and that collection name it as Sn. Okay, this is the collection of all bijections. Bijections are nothing but one to one and onto mappings from S to S. So which is named as Sn. So Sn contains all bijections. Now this Sn with respect to the composition operation, that is composition as the group operation, this forms a group which is called as a permutation group or a symmetric group. Okay, so this is the definition of a symmetric group. Symmetric group is denoted as Sn. So let us take a simple example. You take set with the one symbol, that is you take S is equal to set containing 1. You have to find out now S1. All bijections from S to S. So you have 1 yes. A set has only one element 1. So how many bijections from S to S? That is only 1. So which is that bijection? 1. You can write like this. Means you can write this way also. 1 goes to 1. This bijection is nothing but it is an identity bijection. You can write it as a capital I also. So always mapping is you denoted like this using the arrow diagram, but you can't keep writing the arrow diagram as members of S1. So 1 goes to 1, that is written as this way. 1 goes to 1. This is when you have taken set with the one symbol. Now you take set with the two symbols 1, 2. Now you have to find out S2. S2 means all bijections from S to S. Now S has 1, 2 and another set domain is 1, 2, codomain is also 1, 2. You have to write all possible bijection. One is 1 goes to 1, 2 goes to 2, one bijection. 1, 1, 1, 2, 1, 2, S2, S. So 1 goes to 2, 2 goes to 1. No other possible bijections. So therefore you will get, you have to write the initial elements 1, 2, 1 goes to 1, 2 goes to 2, 1, 2, 1 goes to 2, 2 goes to 1. So now this contains identity element and one more permutation of the elements of 1, 2. Okay, this is S2. Similarly, you get all bijections on S with the 3 symbols, that is S3 equal to. So here the possibilities will be more compared to the previous one. 1, 2, 3. 1, 2, 3. 1 goes to 1, 2 goes to 2, 3 goes to 3. That is identity permutation. That is always there. So 1, 2, 3, 1, 2, 3. Okay. Next, 1 goes to 1. You interchange it. 2 goes to 3, 3 goes to 2. So 1, 2, 3, 1, 3, 2. Next, 1, 2, 3. Interchange this element now. 2. 2, 1, 3. Then 1, 2, 3, 2, 3, 1. Means 1 goes to 2 here, 2 goes to 1, then 3 is fixed, one element you fix. Then 1 goes to 2 over, now 3, 2 goes to 1, 2, 3, 1 goes to 3, 2 goes to 2, 1. Fix one element, 1, 2, 3, 3, 1, 2. Interchange the remaining. So these are all possible permutations on these 3 symbols. So this is called as S3. Okay, S1, S2, S3. S1 has one element, S2 has two elements, S3 has 6 elements. Therefore, Sn has n factorial elements. That is because number of functions, number of bijective functions from S to S is always m factorial if S has m elements. Here S has n elements, so number of elements in Sn, number of all bijections from S to S is equal to n factorial elements. So S4 has 24 elements. 24 elements. So these groups are called as permutation groups or symmetric groups. because they satisfy all condition of a group under the group operation composition. What is the composition operation? See, it is as per the axioms of a group, should be closed with respect to that operation, closure law, then associative law, then identity, existence of identity, and existence of inverse with respect to the composition operation. Let us see one by one. So S1 had only the identity permutation. S2 is equal to, it is 1 2 1 2 and 1 2 2 1. So you can check whether it satisfies all the axioms of the group. So whenever there is only identity element, then it is always a group. Closure law, because 1 1. Okay, composition with 1 1, that is equal to 1 1. 1 goes to 1, 1 goes to 1, 1 goes to 2. See, composition with the second one you take. Identity into 1 to 2 1. 1 goes to 1, 1 goes to 2, so 1 goes to 2. 2 goes to 2, 2 goes to 1, so 2 goes to 1. Similarly, if you take 1 2 2 1, composition 1 2 2 1, so this is equal to 1 goes to 2, 2 goes to 1. So 1 goes to 2, 2 goes to 1, so 1 goes to 1. So 2 goes to 1, 1 goes to 2, 2 goes to 2. So 2 to 1, 1 to 2, so 2 to 2. That element you have to write here below 2. 1 to this first row is fixed. The given elements of the set, yes, n symbols I told. No, here there are two symbols. Then where they'll go after mapping, that you have to write below by applying this composition operation. You can check it satisfies the closure law, and identity is this element itself. Inverse of 1 2 2 1 is inverse of this is itself. Therefore, yes, these are groups with respect to composition as the group operation. You can see here S1, S2, these are abelian groups. They satisfy the commutative property as well. A into B equal to B into A for all A comma B belongs to the given set S1 comma S2. Here there is only one element, so obviously it is abelian. S2 has two elements. You can check with that. Even if you interchange these two, you are going to get the same thing back, because there are just one identity and another element. So S1, S2 are abelian groups. And one thing you have to remember, Sn is non-abelian for all n greater than or equal to 3. Starting from 3, S3, S4, S5, all those permutation groups are non-abelian as well as non-cyclic. They are non-abelian as well as non-cyclic. These two are cyclic groups. It is generated by I, and this is generated by this element 1 2 2 1, because it's when it is squared, it is multiplied two times. Composition taken two times gives you the identity, correct? No, therefore every element is obtained as a power of this element 1 2 2 1. Okay, therefore these two are abelian as well as cyclic. Sn is non-abelian, non-cyclic for all n greater than or equal to 3. So why the name permutation group? Because it gives you all permutations on n symbols. See, what are the permutations on these two symbols? 1 2. One is 1 2, another is 2 1. Correct. Now, this is one arrangement, this is another arrangement. With the three symbols 1 2 3. Here one arrangement, then 1 3 2. 1 2 1 3 2 3 1, then 3 1 2 3 2 1. So these are nothing but the symmetric group elements we have seen just now. So that's why it is also called as permutation on n symbols or bijections from S to S. It gives you all bijections from S to S. And the name symmetric group means, so there is a symmetry, because even permutation and odd permutation, when I explain even and odd permutation, there you will get to know why it is a symmetric group. Means it has exactly half even permutations and half odd permutation. There is a symmetry under permutation. So that's why it is called a symmetric group, and permutation group is nothing but it is giving you permutation on n symbols. So now I told you S3 equal to, we will concentrate from S3, S4 and the remaining symmetric groups, because S1, S2 they are simple, and you know that these S1, S2 are an abelian as well as cyclic. S3, S4 all these are non-abelian, non-cyclic. So S3 elements we had 1, 2, 3, 1, 2, 3, then 1, 2, 3, 2, 1, 3, 2, then 1, 2, 3, 2, 1, 3, 1, 2, 3, 2, 3, 1, then 1, 2, 3, 3, 1, 2, 1, 2, 3, 3, 2, 1. Okay, there are 6 elements now. What is the meaning of this? 1 goes to 1, 2 goes to 2, 3 goes to 3, 1 goes to 1, 2 goes to 3, 3 goes to 2, and so on. All these are nothing but bijections from S to S. So if you name them as F1, F2, these elements, bijections are nothing but functions. So functions, if you name them as either F or alpha, then the first permutation is one of the element. Any permutation or any bijection is an element of this symmetric group. So if you name this permutation as alpha, alpha equal to 1, 2, 3, 1, 2, 3, no. This, let us name it as identity, because it's an identity permutation. This permutation let me name as alpha. Alpha equal to 1, 2, 3, 1, 3, 2. Okay, this means alpha of 1 equal to 1, alpha of 2 equal to 3, alpha of 3 equal to 2. Means name of that function is alpha. From S to S there is a function 1, 2, 3, 1, 2, 3, 1 goes to 1, 2 goes to 3, 3 goes to 2. So alpha of 1 equal to 1. For this function, this is the name of the function, input is 1, output is 1. So alpha of 1 is 1, alpha of 2 is 3, alpha of 3 is 2. So if you name this function, this as f, then you will have f of 1 equal to 2, f of 2 equal to 1, f of 3 equal to 3. So these are elements of the set. First row is always same in all the bijections, because these are the elements of the set, yes. And the second row is nothing but images, where these elements are mapped to. So they are in the second row. So these are nothing but, these are images. Second row represent image of each symbol, and first row represent the symbol. Now see, instead of writing that this way, the arrow diagram for bijections, how we have written it like this. That is where these elements get mapped to. First row fixed and second row is nothing but images. There is one more simple way to represent that. This means each bijection can be represented using cycles or cyclic permutation. Each permutation or each bijection can be written in terms of cycles or cyclic permutation. See, here 1 goes to 1, 2 goes to 2, 3 goes to 3. That is nothing but just the identity permutation, identity bijection. So it is represented like this. Or else we can 1 goes to 1, 2 goes to 2, 3 goes to 3. Okay, but no need to write like this, because they are a single cycle, cycles of length 1. So it is nothing but the identity permutation. Second one, 1 goes to 1. The fixed element is always not written. So 2 goes to 3, 3 goes to 2. You have to just write in the cycle notation as 2, 3. So you can name this as sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and so on. These are all nothing but bijections. So sigma 1 in cycle notation, it is represented as 2, 3, meaning 2 goes to 3 and 3 goes to 2. Then 1 is fixed, 1 is going to 1. No need to write it separately. It is understood that don't write 1 like this. It is understood that in this case 1 is fixed. Similarly, now if you take sigma 2, 1 goes to 2, 2 goes to 1. This means 1 goes to 2, 2 goes to 1. 3 is fixed, no need to write that. Then here it is sigma 3 equal to 1 goes to 2, 2 goes to 3. Okay, here you have to write it completely, because it is a 3 cycle, because 1 goes to 2, 2 goes to 3, then 3 goes to 1, back to 1. That's why the name cycle. Once again, you need to write 1 here. 1 to 2, 2 to 3, 3 to 1. It is like a cycle. That is the meaning of cyclic representation or cyclic notation. And here it is 1 goes to 3, 3 goes to 2, 2 goes to 1, close this. And here it is 1 goes to 3, 3 goes to 1. Okay, so it is just 1, 3, 2 is fixed. So the whole representation changes now. You can write S3 as identity permutation I, then this is 2, 3, and you have 1, 3, then you have one more 2 cycle, 1, 2, then you have 1, 2, 3, then 1, 3, 2. So this is represented as 1, 3, 2 here, and this is represented as 1, 2, 3, and this is 2, 3, this is 1, 2, and this is 1, 3. So the whole symmetric group can be represented easily using the cyclic representation or cycle notation. Then you have to understand what is length of a cycle. Length of a cycle. Okay. See, consider how many elements you have, that you have to count. Here the length of a cycle is 2. Length of a cycle is 2. Here in this case length of a cycle is 2. Here this is of length 3. This is of length 3. This is because sigma m of A equal to A. Then we call it is of a length m. Here in this case sigma 1 of 1 in this case is 2. Sigma square of 1 equal to sigma of 2, which is 3. Then sigma cube of 1 equal to 1. So it is of length 3. You just count how many symbols you have here. 2 symbols, in this case 2 symbols, 1, and here also 3 symbols. They are all of length 2 and 3. Therefore, that is called as a length of a cycle. Now what is a transposition? Transposition. Transposition means it is a cycle of length 2. Okay, it is called as a transposition. See, for example, if you have sigma equal to 1, 2, 3, 3, 2, 1, where this sigma belongs to, this belongs to S3. You have to see the first row. How many elements are there? How many symbols are there here? 3. So it belongs to S3. So sigma in terms of the cycle notation is 1 goes to 3, 3 goes to 1, and one more is 2 goes to 2. Fixed. No, don't write that. Just sigma is represented as 1, 3. So what is the length of this cycle? Length equal to 2. So this is called as a transposition. This is called as a transposition. So any cycle of length 2 is called as a transposition. So S3 has how many transpositions then? One is identity. Identity is not a transposition. So then 1, 2, 1, 3, 2, 3. Okay. Then 1, 2, 3, 1, 3, 2. These are the elements of S3. Here these are transposition. There are totally 3 transpositions. Cycles of length 2 are called as transpositions. Disjoint cycles. Okay, what is this disjoint cycles? See, for example, not giving here mathematical definitions and all. I'm just explaining using example. Disjoint cycle. See here, I'll give you a permutation sigma equal to 1, 2, 3, 4 and 2, 1, 4, 3. This is one of the element of S4. S4 has totally 24 elements. I had given you one permutation or one bijection. So how to write it in cycle notation? 1 goes to 2, 2 goes to 1, 1, 2. 1, 2, 2 goes to 1. Then 3 goes to 4, 4 goes to 3. Now these two are cycles of length 2. There are 2 transpositions. Now these are transposition and these are disjoint cycles. Disjoint cycles because they do not have any element in common or no common symbols. Such cycles are called as disjoint cycles. So every permutation can be expressed as product of disjoint cycles. So this is one permutation, it is expressed as a product of disjoint cycles. Suppose if I give you f equal to 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, this is an element of S9. 3, 4, 2, 1, 6, 5, 8, 9, 7. First write it in cycle notation. 1, 3, 3 goes to 2, 2 goes to 4, 4 goes to 1. Back, close it. Then 5 goes to 6, 6 goes to 5. Okay, then 7 goes to 8, 8 goes to 9, 9 goes back to 7. This is how to write it in cycle notation. Now, all these cycles are disjoint cycles. So, every permutation is written as a product of disjoint cycles. What is the length of this cycle? Count the symbols. 4. Length of this cycle is 2. Length of this cycle is 3. Therefore, this one is transposition. This is of length 4 and this is of length 3. Now one more result, every hour cycle can be expressed as a product of r minus 1 transpositions. R minus 1 transpositions. What is the meaning of this? Suppose I'll give you one R cycle. Here, one 4 cycle. Now, this 4 cycle can be written as the product of 3 transpositions. So, that is how to write starting element and the last element 1 4, then last but one element 1 3, then 1 2. You have to write like this. First element always there fixed, first last but one, then this element. So every R cycle, this is 4 cycle, can be written as a product of 3 transpositions. 4 minus 1 is nothing but 3 transposition. Similarly, 2 3 5. Okay. So this is nothing but 2 goes to 3, 3 goes to 5. So 2, 5 and 2, 3. Product of 2 transposition. This is 3 cycle which is written as a product of 2 transpositions. See, I told you every R cycle can be expressed as a product of R minus 1 transpositions. So, this was the example. This is a 4 cycle. Now, this 4 cycle is represented as a product of 3 transpositions. And there is no unique way of representing it as a product of 3 transpositions. So, you can write like this also 1 2, 1 3. 1 4. You can interchange the positions also. Then also you will get the same permutation. So there is no unique way of representing it as a product of r minus 1 transpositions. Why we can write it as a product of transpositions? Because transposition is a basic permutation. That is, transposition means what? It is swapping any two elements. So every other permutation is product of that basic building block. This acts as a building block now. Transposition acts as a building block because length of a cycle starts from 2 itself. That itself is named as a transposition. See, 1 4 means what? 1 goes to 4. You may think 1 goes to 4, 1 goes to 3, 1 goes to 2. Then it is a mapping. Then how can it go to different element? It is not like that. 1 goes to 4 means in the initial permutation you have to swap 1 and 4. So what you will get? 4 1. Okay, 2 3 as it is. Next, after that, sequentially you have to apply this operation. 1 and 3 swapped in this permutation, so you will get 4 2 1 3. Now within this permutation you have to swap 1 and 2. So swap these two elements, 4 1 2 3. So what is the meaning of this? 1 goes to 2, 2 goes to 3, 3 goes to 4. You are getting the same thing back. Because you know that if you change this cyclically, you are going to get the same permutation. You can write this as 1, 2, 3, 4 as well. Both are same. Just the symbols position is different, but where they go finally that remains same. 1 goes to 2, 2 goes to 3, 3 goes to 4. So if you apply this sequentially, then you are going to get the same thing back. Therefore, every R cycle can be expressed as a product of R minus 1 transpositions, and this expression need not be unique one. So I had explained what is a permutation group. It is a set of all bijections on n symbols. It is denoted as Sn, and Sn has n factorial elements. Okay, Sn is non-abelian and non-cyclic for n greater than or equal to 3. Okay, so how to write S1? It is just the identity. S2 is identity and write it in the cycle notation. 1, 2. 1 goes to 2, 2 goes to 1. Okay, S3 in the cycle notation, because cycle notation helps you to simplify this set Sn. I 1 2 1 3 2 3. Okay, then 1 2 3 and 1 3 2. Totally there are 6 elements. Okay, no commas in between, comma between the elements. This is one element, this is another element, like this. And one more formula you can remember, the number of R cycles in Sn is NPR divided by R. See, as n increases, listing all the elements is difficult because Sn has n factorial elements. See, for up to S3 or S4 it is easy. See, S3 we write it as I, then 1 2, then 2 3, then 1 3, then 1 2 3 and 1 3 2. So it has 2 3 cycles and 3 2 cycles. So number of R cycles, so number of 2 cycles in S3 as per this formula, it is 3p2 divided by 2. So 3p2, 3p2, NPR formula, n factorial divided by n minus R factorial into this R in the denominator. This is the formula of NPR. So 3p2 means 3 factorial by 3 minus 2 factorial. That is nothing but you will get here 3 factorial divided by 2. So that gives you 3. So number of 2 cycles 3. We got the same thing. Similarly, number of 3 cycles, cycles of length 3, it is 3p3. Okay, 3p3 divided by 3 cycles. 3p3 is 3 factorial by 3, which is nothing but 3 3 cancels 2. So you got here 2 3 cycles. As per the formula also, you'll get the same. So number of R cycles in Sn is given by NPR by R. So in S4, if you want to calculate, see S4, 2 cycles. How many 2 cycles in S4? 4p2 divided by 2. So 4 factorial by 4 minus 2 factorial, which is 2 factorial divided by 2. So 4 3 into 2 1, 2 2 cancels, then 2 ones are 2 2, that's 6. There are 6 2 cycles, 6 transpositions in S4. So 3 cycles. How many 3 cycles in S4? 4p 3 divided by 3. 4p3 is 4 factorial by 4 minus 3 factorial. So 4 factorial by 4 minus 3 is 1. 1 factorial into 3. So you'll get 4, then 3, 2, 1 by 3. So cancels 8. You will get 8 3 cycles. So how many 4 cycles? Okay, how many 4 cycles? 4p4 divided by 4. 4p4 means 4 factorial by 4. That is 3 factorial. 6. You will have 6 4 cycles. So 8 plus 6, 14 plus 6, 20. But this S4 has 24 elements. Then which are the other elements? So you will have 3 product of 2 cycles. That is because 1 is identity element. So 23 plus 1 more is identity. Okay, so totally there are 20 plus 1, 21 elements. What are remaining 3 elements? They are product of 2 cycles like this: 1 2 3 4, 1 4 3 2. One more you can add: 1 3 and 2 4. No other possibilities. So all together forms S4. So therefore, I had explained what is a symmetric group, and the notation is Sn, number of elements is n factorial. What is cycle in Sn? Okay. Then what is a transposition? Cycle of length 2. Then every permutation is written as a product of disjoint cycles, and every permutation can also be written as a product of transpositions. R cycle is written as a product of R minus 1 transpositions. So in the next video, I'll explain what is inversion of a permutation, sign of a permutation, as well as how to find order of a permutation. I hope you understood. Thank you for watching.